That's the difference. A gap is answered by a telescope. A crack is answered by a theory. I find this genuinely thrilling rather than worrying, and I want to explain why, because I think the framing usually gets this backwards. Every so often, you'll see a headline saying cosmology is in crisis, with the implication that scientists are floundering. That's a misreading. What's actually happening is that our measurements got precise enough for small disagreements to become visible. For most of the 20th century, the Hubble constant was disputed by a factor of 2. People argued about whether it was 50 or 100, and the error bars were wide enough to hide almost anything. Nobody called that a crisis because with uncertainties that large, nothing could contradict anything. The tension exists now precisely because we got good. The error bars shrank until the disagreement had nowhere left to hide. That's what progress looks like from the inside. Not a smooth accumulation of answers, but a slow tightening of precision until something that used to be comfortably fuzzy becomes unmistakably contradictory. And then, usually, somebody works out what everyone had been quietly assuming. Historically, that's where the big shifts come from. The tiny mismatch in Mercury's orbit that Newtonian gravity couldn't explain wasn't a curiosity to be tidied away. It was the loose thread that general relativity pulled. It looked like an accounting error for decades. So here's the thing I'd leave you with, and it's a way to read science news rather than a fact. When you next see a list of unsolved mysteries of the universe, notice which kind you're being sold. If it's a gap, a place we haven't been, a thing we haven't found, it's genuinely interesting, and the answer will most likely arrive on schedule from a bigger telescope or a longer mission. But if it's a crack, to careful measurements that refuse to agree, a prediction the universe keeps declining to meet, pay closer attention, even when it sounds like bookkeeping, especially when it sounds like bookkeeping, because the mysteries that eventually rearrange physics almost never announce themselves. They don't arrive looking like wormholes or aliens. They arrive looking like two numbers that ought to match and don't. Right now, those numbers are 67 and 73. In 2007, a radio telescope in Puerto Rico detected something weird. A burst of electromagnetic radiation so intense it arrived at Earth in just a millisecond, then vanished completely. The astronomers who found it couldn't explain what they were looking at. They didn't have a name for it yet. Today, we call them fast radio bursts, and we've discovered hundreds of them, yet we still don't know what's causing them. They could be alien signals. They could be neutron stars colliding. They could be exotic physics we haven't even theorized yet. This is the strange reality of modern astronomy. We've mapped billions of galaxies. We've landed rovers on Mars. We've photographed black holes. We've discovered thousands of exoplanets. We understand the universe better than any civilization in history. Yet the more we learn, the more mysteries we uncover. The cosmos is full of phenomena that shouldn't exist according to our best theories. Objects behaving impossibly, structures too large to be real, energy coming from nowhere, matter distributed in ways that make no sense. These are the unsolved mysteries of space, the puzzles that keep astronomers awake at night, the questions that challenge our fundamental understanding of how the universe works. Let me explore them with you. Let me take you to the edges of human knowledge and show you what we don't understand. Fast radio bursts were just the beginning. There's so much stranger stuff out there. First, let's talk about what makes a mystery actually mysterious in astronomy. It's not just something we don't know. It's something that actively contradicts our best models. It's data that shouldn't exist according to our current physics. A true astronomical mystery is an anomaly, and anomalies are where science gets interesting because they point toward deeper truths we haven't discovered yet. Fast radio bursts are a perfect example. When astronomers first detected them, the initial instinct was skepticism. Were they real? Or were they instrumental artifacts, glitches in the equipment creating false signals? But the signals were too clear, too consistent, and they were coming from different directions in the sky, from different times. These weren't equipment errors, these were genuine astronomical events. Yet they shouldn't exist, at least not in the way we were seeing them. The bursts were releasing energy equivalent to millions of times the sun's annual energy output. They were doing it in a millisecond. Then they disappeared, never to be seen again from the same location. What kind of event could do that? A supernova releases enormous energy, but it lasts for weeks or months. A gamma ray burst from a black hole merger lasts for seconds to minutes. But these radio bursts, they lasted less than a second, then were gone. The mystery deepened when astronomers realized something strange about the bursts' patterns. The light was more dispersed at certain frequencies. This meant it had traveled through a lot of material to reach us. The bursts were coming from far away, really far away, billions of light years away. At those distances, the energy calculations became truly absurd. These single millisecond bursts were releasing as much energy as our sun produces in an entire year, from across the universe, in an instant. What could possibly be that powerful, that brief, that distant? Scientists proposed theories. Maybe they were from colliding neutron stars. Maybe they were from magnetars, neutron stars with incomprehensibly powerful magnetic fields, flipping their magnetic configurations. Maybe they were from merging black holes. Maybe they were from exotic matter we hadn't discovered yet. But here's the thing that makes it a real mystery. We found a fast radio burst that repeated. The same burst appeared twice from the same location in the sky, weeks apart. This broke most of our theories. Colliding neutron stars can only collide once. A magnetar's magnetic field reorganization should be a one-time event. These repeating bursts meant the source was still there, still active, still producing these impossible bursts. We've now found dozens of repeating sources, but we still don't know what they are. And that uncertainty is profound. We have an entire class of astrophysical phenomena we can't explain. We measure them, we observe them, we detect them across the galaxy, but we don't understand them. That's where the mystery lies. And that's just the beginning. Let me tell you about pulsars, because understanding pulsars helps us understand why fast radio bursts are so puzzling. Pulsars are neutron stars that spin incredibly fast and emit radiation in a narrow beam. As they rotate, that beam sweeps across Earth like a lighthouse. We detect a pulse every time the beam hits us. Pulsars are already exotic objects. A neutron star is so dense that a sugar cube-sized piece would weigh as much as Mount Everest. All the matter is compressed so tightly that electrons are forced into protons, creating neutrons. It's the most extreme state of matter we can observe directly. Pulsars rotate with incredible regularity. Some complete a rotation in just a few milliseconds. The fastest known pulsar rotates 716 times per second. That's like a city-sized ball of pure neutron material spinning faster than a dentist's drill. The regularity of pulsars is almost perfect. They keep time better than atomic clocks. When the first pulsar was discovered in 1967, It was so regular that astronomers initially thought they'd found alien signals. They called it LGM1 for little green men. But here's where it gets mysterious. Some pulsars are unpredictable. Magnetars are a type of neutron star with magnetic fields billions of times stronger than anything we can create in laboratories. These magnetic fields are so powerful they can slightly distort the spin rate of the star. Magnetars occasionally have outbursts where they release enormous amounts of energy suddenly, almost violently. A magnetar flare can release as much energy in a tenth of a second as our sun releases in a year from across the galaxy. Spontaneously. What causes these outbursts? We don't fully know. Something about the magnetic field configuration seems to snap, releasing energy catastrophically. But the exact mechanism remains mysterious. And this is where fast radio bursts might come in. Some astronomers theorize that fast radio bursts could be signatures of magnetar flares. But the numbers don't quite work out. The energy calculations are off. The timescales don't match perfectly. It's compelling theory, but it's not proven. We're left with a mystery inside a mystery. Magnetars are incompletely understood. Fast radio bursts might come from magnetars, or they might come from something else entirely. We're observing phenomena we can't fully explain, but the mysteries don't stop there. They get weirder. Let me tell you about the Great Attractor. Imagine you're an ant walking on a piece of fabric. The fabric seems flat around you, but unknown to you, there's a massive hole underneath that's pulling everything toward it. Your path curves, and you don't know why. That's what's happening to us, apparently. Our galaxy, the Milky Way, is moving through space at an enormous velocity. We're moving towards something massive, something we can't see directly. We call it the Great Attractor. Here's what we know. The universe as a whole is expanding. Galaxies are receding from us in all directions, but the Milky Way isn't just moving with the expansion, it's moving toward a specific direction in space at a tremendous speed, about 600 kilometers per second relative to the cosmic microwave background. That's incredibly fast. It's as if the entire Milky Way, billions of stars, trillions of planets, is being pulled towards something with enormous gravitational force. But what? We looked in that direction. The Milky Way is being pulled toward the constellation Centaurus. But when we look at the galaxies in that direction, they don't seem massive enough to account for the gravitational pull we're experiencing. So we theorize that there's a hidden attractor, something massive enough to pull an entire galaxy, something we can't see because it's behind the dust and gas of the Milky Way from our perspective, something so gravitationally powerful it's yanking billions of stars through space. It might be a supercluster of galaxies. It might be a concentration of dark matter. It might be something we don't have a name for yet. We can measure the effect. We can calculate the pull, but we can't directly observe the source. It's as if the universe is pulling on us, but we can't see what's pulling. This raises fascinating questions. Are there other attractors we don't know about? Are we being pulled by forces we can't detect? Is the universe full of invisible, massive structures that shape how galaxies move through space? We don't know. And that's the mystery. But wait, there's something even stranger about how matter is distributed in the universe. We've discovered that the universe isn't evenly distributed. Matter isn't sprinkled randomly throughout space. Instead, galaxies form structures. They gather into filaments and walls. They leave vast, empty voids behind. These cosmic voids are mind-bogglingly huge. The Buddha's void is a region of space spanning over 250 million light years that contains almost no galaxies. It's nearly empty, a vast bubble of nothing. How did this happen? Why is the universe organized this way? Our models suggest matter should be distributed more uniformly. Small variations in the early universe should have grown through gravity over billions of years. But these variations shouldn't be this extreme. The universe shouldn't have such dramatic structure, yet it does. We observe walls of galaxies. We observe filaments stretching across billions of light years. We observe voids so enormous that our imagination struggles to grasp their scale. Why is matter distributed this way? The honest answer is we don't fully understand. We have models that partially explain it, but the universe's structure is more dramatic than our theories predict. It's another mystery. Another indication that we don't understand the universe as deeply as we thought. Let me shift to a different kind of mystery. The planets we're discovering are breaking all our rules. When we started finding exoplanets in the 1990s, we expected to find planets like ours, rocky inner planets, gas giants in the outer solar system, a nice, orderly arrangement like we see around the sun. Instead, we found hot Jupiters, massive gas giants orbiting closer to their stars than Mercury orbits the sun. These shouldn't exist according to our planetary formation models. Gas giants should form far from their stars where it's cold enough. They shouldn't be close to the star. But there they are, hundreds of them. Planets that, according to our models, shouldn't be there. We've proposed migration theories. Maybe the gas giants form far out, then migrate inward due to interactions with the protoplanetary disk. It's a reasonable theory. But the fact that our original models were completely wrong about this common configuration shows how much we don't understand about how planets form. Then there are the rogue planets. These are planets that aren't orbiting any star. They're wandering through interstellar space alone, isolated, orbiting nothing. How did they form? Did they form around stars and get ejected? Are they the only planets that ever existed and their stars dissolved? We don't fully know. We've estimated that there might be trillions of rogue planets in our galaxy alone. Trillions of worlds drifting through space, going nowhere, orbiting nothing. It's a haunting thought. A vast population of worlds we can barely detect, hidden in the darkness between stars. But how did they get there? What were their origins? The mystery deepens. There's also a mystery about planetary habitability. We've discovered exoplanets in the habitable zone, the region around their star where liquid water could exist. But when we look at those planets, many of them shouldn't be habitable. Some are tidally locked, with one side always facing their star and one side always in darkness. The daylight side would be a scorching hellscape. The night side would be a frozen wasteland. How could life exist there? Yet if life developed in the twilight zone, where day meets night, protected by atmosphere and water, maybe it could survive. Maybe our definition of habitability is too narrow. Maybe the universe has life in places we don't expect. Or maybe we're completely wrong about what makes a planet habitable. Maybe life, if it exists, is far more robust and adaptable than we imagine. Maybe planets we consider uninhabitable are actually teeming with life. We don't know. And that's a profound mystery. Let me tell you about something called the lithium problem. It sounds obscure, but it points to something fundamental we might be missing about stellar physics. When the universe formed, the Big Bang created certain elements, hydrogen and helium primarily, plus tiny amounts of lithium and beryllium. The amounts were predicted by Big Bang nucleosynthesis models. We know what those predictions are. They're well tested, Then we look at the oldest stars in the galaxy and measure their lithium content. The lithium should match the Big Bang predictions. It doesn't. There's about 1,000 times less lithium in old stars than there should be. It's as if something is consuming the lithium, or it's not being created in the Big Bang as much as we think. Where did the lithium go? It's not being destroyed in the stars. The physics doesn't work out. It's not being created elsewhere. Nothing explains the discrepancy. This is called the lithium problem, and it remains unsolved. We have measurements that don't match our theories. We have an abundance of an element that's way too low to make sense, and we don't know why. This might seem like a small thing, one element, one discrepancy, but in physics, every discrepancy matters. Every mismatch between prediction and observation points to something we don't understand. Something fundamental might be wrong with our models. The lithium problem suggests that either we don't understand the Big Bang as well as we think, or we don't understand stellar physics as well as we think, or both. And that's concerning because both are central to how we understand the universe. This is where mysteries matter. They're not just curiosities, they're cracks in our understanding. Places where the universe is telling us we're missing something crucial. Let me tell you about cosmic rays, which are another profound mystery. Cosmic rays are high-energy particles traveling through space at nearly the speed of light. They bombard Earth constantly. They come from space, pass through our atmosphere, and hit us regularly. We don't know where most of them come from. That's the mystery. We've identified some sources. Supernovae send out cosmic rays. The sun emits cosmic rays during solar flares. Pulsars and magnetars probably produce cosmic rays. These explain maybe 10% of the cosmic rays we observe. But where do the other 90% come from? We don't know. They're just arriving at Earth from random directions, carrying energy far beyond what our known sources should produce. The highest energy cosmic rays are especially mysterious. We've detected cosmic rays with energy levels so high they shouldn't exist. An extremely high energy cosmic ray hitting Earth's atmosphere creates a cascade of secondary particles. If we measure that cascade, we can calculate the original cosmic ray's energy. Some of these energies are incomprehensibly large. One cosmic ray, the Oh My God particle detected in 1991, had energy equivalent to a baseball traveling at 90 miles per hour. But compressed into a subatomic particle, the energy density was insane. Where did it come from? How was it accelerated to such extreme speeds? The most powerful natural accelerators we know, supernova shockwaves and pulsar magnetospheres, shouldn't be able to reach these energies. Something is creating cosmic rays more powerful than our best theories predict. Something unknown is accelerating particles to incomprehensible speeds, and we have no idea what it is. This is genuinely mysterious. We detect particles with impossible energy levels. We measure them. We observe them. But we can't explain how they got that way. There's something accelerating cosmic rays that's beyond our current physics. Let me talk about another mystery that connects to something stranger. The three-body problem. In physics, we can predict how two objects orbit each other. The math is solved. We know exactly how binary stars behave, how planets orbit stars, how moons orbit planets. But add a third body, and the system becomes chaotic. We can't predict exactly how it will behave. Small changes in initial conditions lead to wildly different outcomes. The system becomes fundamentally unpredictable. This is the three-body problem. It's not that we don't know enough math, it's that the problem is mathematically chaotic. The future states of three bodies orbiting each other cannot be predicted perfectly, even with infinite computational power. So, what's the mystery? The mystery is that the universe is full of three body systems. We have binary star systems with planets orbiting them. We have triple star systems. We have hierarchical systems with multiple planets and moons. These shouldn't be stable. According to chaos theory, they should drift apart or collide, yet they persist. Many three body systems are stable despite being chaotic. How? What mechanism keeps them from flying apart? Why do we observe stable three body systems when the math says they should be fundamentally unpredictable? There are answers: hierarchical organization, resonances, specific orbital configurations. But the full picture remains mysterious. We don't completely understand why stable three-body systems exist or how common they are. And this matters because most planets probably exist in multi-star systems or have multiple moons or exist in complex gravitational environments. Understanding these systems is crucial to understanding where life could exist. Yet the math says these systems should be chaos. We observe that they're often stable. The discrepancy is a mystery. Let me tell you about something even more fundamental. We don't know how planets form. This might sound ridiculous. We've landed rovers on planets. We photographed exoplanets directly. We understand planetary physics. How can we not know how planets form? But it's true. The details of planetary formation remain poorly understood. We know the basic outline. A protoplanetary disk forms around a young star. Dust grains collide and stick together, forming larger and larger particles. Eventually you get planetesimals, then planetary embryos, then planets. But the details? They're a mess. There's something called the dust barrier problem. Particles of a certain size, millimeter to centimeter sized, don't stick together efficiently. They should drift into the star instead of growing into planets. But planets form, so something is preventing the dust from drifting inward. We don't know what. Maybe magnetic fields, maybe turbulence, maybe gravitational instability. We have theories, but we don't have proof. There's also the planet trap problem. For planets to grow, they need to be in specific orbital zones. But our models suggest planets should quickly drift out of these zones. They should spiral into the star. Yet planets form and stay in place. Again, we don't fully understand the mechanism that prevents this. We also don't understand planetary migration. Hot Jupiters exist. That means planets have moved after forming. They've migrated inward or outward significantly. But how far? How fast? What determines how much they migrate? This matters because planetary migration affects where planets end up. It determines the system's final architecture. If planets migrate more than we think, the implications for habitability are profound. Planets in the habitable zone might not have formed there. They might have migrated from elsewhere. We're discovering that planetary systems are more dynamic than we imagined. Planets move, they interact, they change their orbits over time, but we don't fully understand the mechanisms. This is a profound mystery because planetary formation is central to everything. It's how worlds form. It's how habitable planets form. And we're discovering we don't understand it nearly as well as we thought. Let me shift to a different mystery: the nature of dark matter and dark energy. These aren't exactly space mysteries per se, but they're mysteries about the universe that space observations revealed. Dark matter is invisible stuff that makes up about 85% of all matter in the universe. We can't see it. We can't touch it. We know it exists because of its gravitational effects. Galaxies rotate too fast. Galaxy clusters hold together too tightly. Something massive is there providing gravity, but we can't detect it directly. What is it? We don't know. We have candidates: weakly interacting massive particles, axions, primordial black holes, sterile neutrinos. We have ideas, but we haven't detected dark matter directly. This is a profound mystery. We've mapped the universe. We know where dark matter is. We know how much there is, but we don't know what it is. It's as if the universe is telling us there's a massive piece of physics we're missing. Dark energy is even stranger. It makes up about 68% of the universe's total energy density. It's causing the universe's expansion to accelerate. Distant galaxies are receding faster as time progresses. Something is pushing space apart. But what? We call it dark energy. But that's just a name. We don't know what it is. We have candidates. The cosmological constant, quintessence, modified gravity. But we don't know. And here's the strangest part. The ratio of dark matter to dark energy is roughly 3 to 2. It's a near coincidence that we're living in a universe where these two components are similar in magnitude. This is called the coincidence problem. Why is the ratio so close to 1? If dark matter and dark energy had formed at different times or through different mechanisms, you'd expect their ratio to be wildly different. But they're similar, nearly equal. It seems like too much of a coincidence. Is it really a coincidence? Or does it hint at something deeper? Some unified theory of dark matter and dark energy? Some principle we haven't discovered yet? We don't know. And that's the mystery. But let me tell you about something more immediate and perhaps even more mysterious: interstellar objects. For decades, we assumed all objects in our solar system formed here. Asteroids formed from material around the young sun. Comets formed in the outer solar system. Nothing came from outside. Then in 2017, we detected an object falling into our solar system from interstellar space. We called it Oumuamua. It came from outside, passed through our solar system, and left, heading back out to the stars. You should see it. Its properties were strange. It was extremely elongated, like a cigar or a pancake. Its composition was unusual. It accelerated as it left the solar system in a way that didn't match the sun's gravity alone. Some astronomers proposed that it might be a solar sail, a spacecraft from an alien civilization. Others said it must be outgassing, ejecting material that provided extra propulsion. Still others said it was just a weird asteroid. We still don't know for sure. Oumuamua left our solar system. We can't study it anymore. We can only guess about its nature based on the brief observations we had. But it raised a profound question. Are interstellar objects common? Is the space between stars full of wandering bodies? Are there objects passing through our solar system regularly that we've never detected? We've now found a few more interstellar objects. Comet Borisov visited a few years ago. It had properties suggesting it came from a red dwarf star system. How many are out there? What are they? Where did they come from? We don't know. These wanderers from the stars are a mystery we're only beginning to understand. Let me tell you about the missing satellite problem, which is a puzzle about our own Milky Way. Our models suggest that the Milky Way should have many more satellite galaxies than we observe. Based on how galaxies form, there should be hundreds of dwarf galaxies orbiting us. But we only see a few dozen. Where are they? Did they get destroyed? Did they not form for some reason? Do they exist, but we can't see them because they're too dim? This is called the missing satellites problem. And it's a genuine mystery. Our models predict something we don't observe. The universe is not behaving as we expected. Recent observations have found more satellites, but not nearly enough to match the models. We're still missing the majority of the satellites we'd expect to see. This suggests something is wrong. Either our models of galaxy formation are incorrect, or there's some mechanism destroying or hiding satellites. Or the satellites didn't form for reasons we don't understand. Again, a discrepancy. Another crack in our understanding. Let me talk about something even stranger: fast-moving stars. We've discovered stars orbiting the galactic center so quickly and so closely that it shouldn't be possible. They're moving faster than the gravitational equations allow. They're getting closer to the black hole than physics predicts is safe. These stars are experiencing gravitational forces that should tear them apart. Their tidal forces should overcome their internal gravity. The black hole's gravity should rip them to shreds. Yet they survive. They orbit. They endure. How? There's something about the physics we don't understand. One possibility is that these stars have particularly compact, dense cores that can withstand the tidal forces. But we don't fully understand their structure. Another possibility is that there's something wrong with our gravitational models at these extreme scales. Or maybe the stars are younger than we think and formed in place. Or they're the remnants of collisions between other stars. We have theories, but we're not certain. This is a mystery at the heart of our galaxy. Stars behaving impossibly near the supermassive black hole. Let me tell you about something else we don't understand: how massive stars form. We understand how stars like our sun form. We have good models. But how do the really massive stars form? The ones with dozens or hundreds of solar masses. These stars radiate enormous amounts of power. The radiation pressure is so strong it should blow away the infalling material. The star shouldn't be able to grow past a certain size because radiation pressure should stop the accretion. But massive stars exist. They're real. We observe them. They formed somehow despite physics saying they shouldn't. How? We don't know. Maybe they formed through collisions between smaller stars. Maybe there's a mechanism that reduces radiation pressure. Maybe our models are missing something fundamental about how massive stars form. It's another mystery. Another case where observation contradicts theory. Let me tell you about exoplanet mysteries. We've discovered thousands of exoplanets now. We know they exist. We can observe them. We can measure their properties. But many of their properties make no sense. We have planets around red dwarfs that seem too large to have formed there. We have planets in highly eccentric orbits that should have been ejected. We have planets in configurations that violate our models of planetary formation and migration. Each discovery expands our ignorance. Each new exoplanet reveals another way the universe violates our expectations. We also don't understand how common certain types of planets are. We detect many super-Earths and mini-Neptunes. These are planet types that don't exist in our solar system. They should be easy to find if our models are right. But they're more common than our models predict. We also don't understand planetary atmospheres. Some exoplanets should lose their atmospheres due to stellar radiation, yet they retain them. Some shouldn't have atmospheres at all based on their properties, yet observations suggest they do. Our models of planetary atmospheres are incomplete. We're discovering that atmospheres are more robust and varied than we expected. Let me tell you about something that touches on the possibility of life: extremophiles and the nature of habitability. We've discovered organisms on Earth that survive in conditions we thought impossible. bacteria in boiling hot springs, organisms in radioactive waste, life in the deepest ocean vents, tardigrades surviving in the vacuum of space. This expands our conception of where life could exist. If life can survive these extreme environments on Earth, maybe life on other worlds isn't as restricted to habitable zones as we thought. Maybe life exists in the clouds of Venus. Maybe life exists under the ice of Europa or Enceladus. Maybe the universe is teeming with life in places we never thought to look, but we don't know. Extremophiles show us that life is robust. But how robust? How much variation from Earth conditions can life tolerate? We don't fully understand the limits. This is a mystery because it affects where we should search for life. If our conception of habitability is too narrow, we might be looking in the wrong places. Let me talk about gravitational waves, which are ripples in space-time itself. They were predicted by Einstein's relativity but weren't directly detected until 2015. Now we detect them regularly. Merging black holes, colliding neutron stars. These events produce gravitational waves that ripple across the universe. We can measure them. We can detect them from billions of light years away. But here's the mystery. Some of the gravitational wave events don't match our models. We've detected black hole collisions that produce black holes larger than our models predict possible. We've detected merging systems with properties we didn't expect. It's as if the universe is making black holes and neutron stars that shouldn't exist according to our stellar evolution models. How did they form? What evolutionary paths led to these unexpected systems? We don't know. Gravitational wave astronomy is revealing that stellar and black hole evolution is more complex than we thought. Let me talk about the Yarkovsky effect and how it affects our understanding of asteroid and planetary motion. The Yarkovsky effect is a subtle phenomenon where radiation pressure from the sun causes small objects to drift gradually through space. Asteroids are warmed by the sun on one side. They radiate heat. The heat radiation has a slight directional bias that causes the asteroid to accelerate slightly. Over millions of years, this tiny acceleration adds up to significant orbital drift. This matters because it affects where asteroids end up. It changes their orbits. It could send them spiraling into planets or out of the solar system. But here's the mystery. We don't fully understand how efficient this effect is. The calculations depend on the asteroid's material properties, its rotation, its surface characteristics. Small changes in these assumptions lead to wildly different predictions. This means we don't fully understand how asteroids behave over long timescales. We don't fully understand the dynamics of small bodies in our solar system. This matters for understanding the solar system's history. It matters for predicting impacts. It matters for understanding how planetary systems evolve. Yet the Yarkovsky effect remains partially mysterious. We understand the basic physics, but the details remain uncertain. Let me tell you about something called the lithosphere and how little we understand planetary magnetic fields. Earth has a magnetic field generated by molten iron in its core. This field protects us from solar wind. It's essential for life. But we don't fully understand how planetary magnetic fields work. We don't know why some planets have them and others don't. We don't know how stable they are. We don't know how they change over time. We also don't understand planetary interiors. We know Earth has a core, mantle, and crust, but the exact structure, the exact composition, the exact processes happening inside, partially mysterious. This matters because planetary interiors affect climate, geology, habitability. If we don't fully understand planetary interiors, we don't fully understand planets. And this connects to a broader mystery. We don't understand how planets become habitable. What specific conditions, what specific processes, what specific characteristics make a planet capable of hosting life? We have ideas: liquid water, magnetic field, stable climate, proper distance from star. But how essential is each factor? What other factors matter that we haven't considered? We're discovering that planetary habitability is more complex than we thought. Planets we considered uninhabitable might have conditions suitable for life. Planets we considered promising might have hidden problems. The universe is more complex than our models, and that complexity reveals our ignorance. Let me shift to one more mystery before we conclude: the nature of time itself and how it relates to space. Einstein showed that time and space are interconnected. They're not separate, they're part of a unified space-time. But we still don't fully understand time. Is it fundamental, or does it emerge from something deeper? What determines time's direction? Why does time always move forward? At the subatomic level, quantum mechanics is indifferent about time direction. The equations work equally well forward and backward, yet macroscopically time flows in one direction only. This is deeply mysterious. Something fundamental about the universe breaks time symmetry. But what? How? We don't fully know. This matters because understanding time matters for understanding everything. Time underlies physics. It underlies chemistry. It underlies biology. If we don't fully understand time, we don't fully understand the universe. And this connects to our very last mystery: the nature of consciousness and observation. Quantum mechanics has an observer effect. Observation affects the outcome of experiments. But what is an observer? Does it need to be conscious? Does it need to be an intelligent being? Or is any measurement an observation? The answer matters because if consciousness affects quantum mechanics, then consciousness is fundamental to physics. Consciousness isn't just an emergent phenomenon, it's woven into the fabric of reality. But we don't know. This remains one of the deepest, most philosophical mysteries in physics. And it's connected to space and astronomy because the universe itself is the ultimate quantum system. We're observing the universe. Our observations affect what we can know about it. We're part of the system we're studying. How do we untangle this? How do we understand objective reality when our observation is intertwined with that reality? Let me tell you about the mysteries of stellar binary mergers. When two stars orbit closely enough, tidal forces can tear them apart. They merge. When this happens, it's violent. It releases enormous energy. But we don't fully understand binary mergers. We don't know what happens in the merger. We don't know what the final product is. Is it a single star, a nebula, something exotic? Our models produce different predictions. Our observations show mergers happening, but the details remain mysterious. Let me tell you about the mysteries of interstellar medium. The space between stars isn't empty. It's filled with gas and dust. This gas and dust has complex structure, but we don't fully understand that structure. We don't understand how dust forms. We don't understand how gas is organized. We don't understand the magnetic fields that pervade the interstellar medium. And there are mysteries about the gas. Cosmic dust absorbs light. But the exact composition of that dust? Partially mysterious. The dust grains are made of silicates and carbon. But in what proportions? With what properties? We don't fully know. Let me tell you about the mysteries of galactic structure. Galaxies have spiral arms. But why? What causes the spiral structure? We have density wave theory. It suggests that spiral arms are density waves, areas of slightly higher density that persist as the galaxy rotates. But the theory has problems. It predicts the spiral arms should be wound up tighter over time. Yet we observe well-defined spiral arms in galaxies billions of years old. How do the spiral arms persist? Why aren't they wound up? There's something about the physics we don't understand. Let me tell you about the mysteries of galaxy cores. Galaxies have central regions that are mysterious. Most galaxies have supermassive black holes at their centers. But how do the black holes and galaxies co-evolve? Do the black holes affect galaxy formation? Does galaxy formation affect black hole growth? We don't fully understand the relationship, and some galaxies have active nuclei, regions that are extraordinarily bright. Jets shoot out at nearly the speed of light. Enormous energy is being released, but the exact mechanisms remain mysterious. Let me tell you about the mysteries of the intergalactic medium. Between galaxies is a vast expanse of gas called the intergalactics. Medium. It's mostly invisible. We only detect it indirectly, but it's out there. It's absorbing light from distant objects. This absorption creates features in the spectra we observe. These are called Lyman alpha forest features, but the intergalactic medium has mysteries. We don't fully understand its structure. We don't understand how it's organized. We don't understand how it evolved over cosmic time. The universe has an enormous reservoir of gas between galaxies, but we barely understand it. Let me tell you about the mysteries of the cosmic microwave background. The cosmic microwave background is radiation left over from the Big Bang. We observe it. We measure its temperature. We study its patterns. But mysteries remain. The CMB has anomalies. There are features in the pattern that don't match predictions, cold spots that shouldn't be there, asymmetries that suggest the universe might not be isotropic. Are these real features? Or are they statistical flukes? Do they point to new physics? Or are they just noise? We don't know. Let me tell you about the mysteries of cosmic expansion. The universe is expanding. We know this from observations of distant supernovae showing that expansion is accelerating. But how accurate are those observations? Are there systematic errors? Have we misinterpreted the data? Different methods give slightly different expansion rates. The tension between measurements is concerning. Something might be wrong with our understanding. Or maybe the expansion rate is varying. Maybe dark energy is changing with time. Maybe the universe's expansion is more complex than we thought. Let me tell you about gravitational lensing, which is one of the strangest phenomena in space. When light passes near a massive object, like a black hole or a galaxy cluster, the object's gravity bends the light. The light follows a curved path. This is cool. We can use it to see objects we couldn't otherwise see. We can magnify distant galaxies. We can study the universe in ways that would be impossible without gravitational lensing. But here's the mystery. Sometimes we see multiple copies of the same object. The same distant galaxy appears in multiple places in the sky because light from that galaxy took multiple paths around the intervening object. We can measure how long it took for light to travel each path. The paths are different lengths, so light from different paths takes different times to reach us. This means we're seeing the galaxy as it was at different times. We're seeing the past. We're seeing events from different epochs. And here's the mystery. We can't always figure out which image is which. Which is the original? Which are the copies? The geometry gets complicated, and there's another mystery within this mystery. Sometimes the galaxy images appear to change brightness at different rates, as if the galaxy itself is varying. But wait, we should be seeing the same galaxy at different light travel times. The brightness changes should be correlated. If the galaxy got brighter, all images should get brighter, just at different times. But sometimes the images vary independently, as if they're responding to different things. This suggests something else is going on. Some effect we don't fully understand is happening with the light. This points to a deeper mystery. We don't fully understand how light propagates through the universe. We don't fully understand what happens to light as it travels billions of light years through space and past massive objects. Let me tell you about moon formation mysteries. How moons form is largely mysterious. Our moon is huge compared to Earth. It's about 1/4 Earth's diameter. No other planet has a moon so large relative to its size. How did this happen? Our current theory is the giant impact hypothesis. An early Mars-sized object collided with Earth when the solar system was young. This impact ejected material into orbit. That material coalesced into the moon. But this theory has problems. The impact would have to be incredibly precise. The angle would have to be just right. The masses would have to balance perfectly. It seems unlikely that this happened by chance. And when we examine the moon's composition, it has a different isotopic ratio than Earth. This is suspicious. If the moon formed from material ejected from Earth, the isotopes should match more closely. So where did the moon really come from? Maybe from the impactor. But then the isotopic ratios don't match the impactor either. Maybe the moon didn't form from a single impact. Maybe it formed from multiple collisions or gradually accumulated from debris. Maybe it didn't form in Earth's orbit at all, but was captured from elsewhere. We don't know. The moon's origin remains mysterious. Let me tell you about comet mysteries. Comets are icy bodies from the outer solar system. They have beautiful tails. They're made of ice and rock. They follow orbits around the sun. But we don't fully understand how comets behave. Some comets outburst, suddenly become brighter, for unknown reasons. They might fracture. They might eject material. But the exact triggers remain mysterious. We also don't understand comet composition. Comets seem to be made of different materials in different places. Some are icy, some are rocky, some are carbonaceous. There's diversity we can't fully explain, and there's a mystery called the fading comets problem. Some comets should return to the inner solar system periodically, but when we look for them at their predicted times, they're not there, or they're much fainter than expected. What happened to them? Did they fragment? Did they change orbits? Do we not understand their dynamics? Let me tell you about the mysteries of dark matter itself in more detail. We know dark matter exists because galaxies move as if there's more matter than we can see. The rotation curves don't match. The orbital velocities are too high. Something massive is there. But what is it? This is one of the biggest mysteries in physics. We've searched for particles. We've looked for dark matter candidates. We haven't found any. We've searched using direct detection experiments, hoping dark matter particles will collide with atomic nuclei. We detect trillions of cosmic rays every year. But dark matter particles? Nothing. We've looked using indirect detection, searching for the signatures of dark matter particle annihilation, We should see gamma rays or other radiation if dark matter particles destroy each other. But the signals are ambiguous or absent. We've looked using collider experiments trying to create dark matter particles in high energy collisions. We haven't found them. Where is it? What is it? The universe is full of this mysterious substance, but we can't detect it directly. We can only infer its presence from its gravitational effects. Some physicists have proposed modified gravity theories. Maybe there's no dark matter. Maybe gravity works differently at large scales. Maybe the inverse square law breaks down at galactic distances. But our best observations support dark matter, not modified gravity. We've tested modified gravity and found it doesn't work. Dark matter remains the best explanation. But we still don't know what it is. Let me tell you about dark energy in more detail as well. Dark energy is causing the universe to expand faster. Distant galaxies are receding faster than they should be based on ordinary gravitational deceleration alone. What's pushing them? We don't know. We call it dark energy, but that's just a label. Dark energy makes up 68% of the universe. It's the dominant component, yet we know almost nothing about it. We don't know if it's a particle. We don't know if it's a field. We don't know if it's a property of space-time itself. The cosmological constant is our best guess. Einstein proposed it as a constant density of energy pervading all space. It pushes space apart. It causes acceleration. But if that's true, it should have a value determined by quantum field theory. When we calculate what that value should be, we get a number that's 10 to the power of 122 large. By the largest discrepancy in physics. How can we get that so wrong? What are we missing? This is the cosmological constant problem. One of the deepest mysteries in physics. The universe's expansion is driven by something we don't understand, with a value we can't calculate that should be wrong by 120 orders of magnitude. Yet the observations are clear. The universe is accelerating. Dark energy is real. So something fundamental is wrong with our understanding. We're missing a huge piece of the puzzle. Let me tell you about stellar composition mysteries. Stars are made of hydrogen and helium primarily, with traces of heavier elements, but we don't always find the ratios we expect. Some stars are metal-rich, some are metal-poor, some have unusual elemental abundances. Why? We have theories. These stars form from clouds of gas with particular compositions. The composition depends on what's in the interstellar medium. Heavy elements accumulate over time as stars explode and seed new generations with heavier elements. But some stars don't fit these patterns. Some old stars are metal-rich. Some young stars are metal-poor. Some have peculiar abundances that don't match our models. It suggests that stellar evolution and galactic chemical evolution are more complex than we understand. Let me tell you about binary star mysteries. Many stars have companions. They're binary systems, two stars orbiting each other, but binary stars often have unexpected properties. Some have extremely eccentric orbits that shouldn't be stable. Some are tilted in strange ways. Some have rotations that don't align with their orbital plane. This suggests that binary star formation and evolution involve processes we don't fully understand. And some binary systems produce phenomena we can't explain. Eclipsing binaries that have timing variations, X-ray binaries with jets we don't fully understand, contact binaries that are somehow sharing material in ways that violate our models. The universe is making binary stars that don't fit our theories. Let me tell you about supernovae in more detail. Type 1. A supernovae are white dwarfs that steal material from companion stars. The material accumulates on the white dwarf surface until the pressure and temperature become so extreme that thermonuclear fusion ignites across the entire surface. But here's the mystery. This process should produce nuclear ash with particular isotopic ratios. When we observe the ash in the explosion, the ratios are wrong. We're not producing the isotopes we should be producing. This suggests either that the explosion process is different than we think, or that our understanding of nuclear burning is incomplete. And type 2 supernovae, the explosions of massive stars, are even more mysterious. We know the basic outline. The star's core becomes so dense that electrons are forced into protons. A neutron star forms. The material in falling onto the neutron star bounces back and creates a shock wave. Incredible. But the details. How exactly does the shock wave propagate? How does it manage to escape the star? Our computer simulations have trouble recreating supernovae explosions with the observed energies. Something about the physics isn't right. Let me tell you about neutron-star merger mysteries in more detail. When two neutron stars orbit each other closely, their mutual gravitational attraction radiates away energy as gravitational waves. They spiral inward. Eventually, they collide. When they collide, they release an enormous amount of energy. They produce gravitational waves. They produce X-rays, they produce gamma rays, they produce all kinds of radiation, and they produce our process elements. These are heavy elements like gold, platinum, and uranium. We think neutron-star mergers are the primary source of our process elements in the universe. But here's the mystery. We're not producing enough our process elements in neutron-star mergers to account for the amounts we observe in the galaxy. We need something else, some other source, some process we haven't identified, or maybe our models of neutron-star mergers are wrong. Maybe the mergers produce more our process elements than we think, but our computer simulations don't support that. We're discovering that we don't fully understand nucleosynthesis in neutron-star mergers. We don't fully understand where the heavy elements come from. Let me tell you about cosmic distance measurement mysteries. Measuring distances to distant objects is crucial for cosmology. It determines the size of the universe. It determines cosmic expansion rates. It determines whether dark energy is real. We use standard candles, objects with known brightness. Supernovae are standard candles. We measure how bright they appear from Earth. From that, we calculate how far away they are. But here's the mystery. Not all supernovae have the same brightness. Some are brighter. Some are dimmer. We've developed methods to standardize them, but the standardization itself is empirical. We don't fully understand why supernovae vary in brightness. If we don't understand this, our distance measurements might be wrong. Our entire cosmic distance scale might be off. The expansion rate of the universe might be different than we think. Dark energy might be stronger or weaker than we measure. It's a profound uncertainty at the foundation of cosmology. Let me tell you about the mysteries of time itself. Einstein showed that time and space are interconnected. They're not separate, they're part of a unified space-time. But we still don't fully understand time. Is it fundamental, or does it emerge from something deeper? What determines time's direction? Why does time always move forward? At the subatomic level, quantum mechanics is indifferent about time direction. The equations work equally well forward and backward. Yet macroscopically, time flows in one direction only. This is deeply mysterious. Something fundamental about the universe breaks time symmetry. But what? How? We don't fully know. This matters because understanding time matters for understanding everything. Time underlies physics, it underlies chemistry, it underlies biology. If we don't fully understand time, we don't fully understand the universe. These are the unsolved mysteries of space. Fast radio bursts that we can't explain, the great attractor pulling galaxies, pulsars and magnetars with incomprehensible physics, planetary systems that violate our models, dark matter and dark energy that make up 95% of the universe but whose nature we don't know, cosmic rays with impossible energies, three-body systems that shouldn't be stable but are, planetary formation processes we don't fully understand. The list goes on. The universe is stranger than we imagined, and every mystery points to something deeper. Every discrepancy between prediction and observation suggests physics we haven't discovered yet. This is the frontier of science. This is where discoveries happen. This is where the next revolution in our understanding might emerge. Some of you watching this might help solve these mysteries. You might become an astronomer who figures out what fast radio bursts are. You might become a physicist who explains dark matter. You might become an explorer who discovers life on another world. The mysteries await. The universe waits to be understood. And the adventure continues. Let me dive much deeper into some of these mysteries because they deserve more exploration. Fast radio bursts remain one of the most perplexing phenomena we've discovered in the modern era of astronomy. We've detected hundreds of them now. Each one is a brief flash of radio energy that tells us something profound about a process we don't understand. The energy output is incomprehensible. Think about the sun. The sun releases an enormous amount of energy every second. It has been burning for billions of years and will continue for billions more. It's an unimaginably powerful object. Now imagine an event so energetic that it releases as much energy in a millisecond as the sun releases in an entire year. That's a fast radio burst. Now imagine that this event is happening billions of light years away. Now imagine that there are hundreds of them happening across the universe. Now imagine that we still don't know what they are. The most puzzling aspect is the repeaters. Some fast radio bursts repeat. The same source produces bursts multiple times. Some repeat randomly. Some repeat in patterns. FRB 180916 repeats with a 16-day cycle. Every 16 days it turns on, produces bursts for several hours, then turns off. Clockwork precision. What would cause this? The leading theory is a binary system, a neutron star orbiting something. As it orbits, the orientation changes. Sometimes the emission cone points toward us. Sometimes it points away. But if that's true, then the binary must be incredibly precise. The orbital mechanics must create exactly this pattern. But we don't know if there's an accretion disk. We don't know if there's a companion. We don't know if it's actually a binary at all. We're speculating based on patterns we observe. Let me tell you about pulsars because they connect to fast radio bursts. Pulsars are neutron stars that rotate incredibly fast. The fastest known pulsar rotates 716 times per second. That's a city-sized ball of neutron matter spinning faster than a power drill. It's incomprehensibly fast. Yet these objects are so regular that they keep time better than our atomic clocks. They're remarkably predictable. But magnetars, a special type of neutron star with extreme magnetic fields, are unpredictable. They suddenly release enormous energy in flares that last fractions of a second. Oh, Magnetar can release more energy in zero point 0.1 seconds than our sun releases in a year. From across the galaxy, spontaneously, with no warning. We don't understand what triggers these flares. Something about the magnetic field configuration seems to snap catastrophically. But why? When does it happen? We can't predict. Let me tell you about black holes in more detail. Black holes are regions where gravity is so extreme that nothing can escape. Not matter, not radiation, not light. But black holes themselves are mysterious in multiple ways. First, there's the question of formation. How do black holes form? Stellar mass black holes form from the collapse of massive stars. But supermassive black holes, millions or billions of solar masses, present a puzzle. How did they grow so large? If they form from stellar mass black holes merging, the growth would take a very long time. Mergers are rare. Getting from stellar mass to galactic mass would require incredible patience and improbable luck. Some theorists propose that supermassive black holes form directly from massive clouds in the early universe. But this requires physics we don't fully understand. Second, there's the information paradox. Black holes evaporate through Hawking radiation. But if a black hole evaporates completely, what happens to the information that fell into it? Information should be conserved according to quantum mechanics. But black hole evaporation seems to destroy information. This is a genuine paradox between general relativity and quantum mechanics. Something fundamental is wrong with our understanding of physics at the scale of black holes. Third, there are black hole mysteries we observe directly. We've detected black hole collisions through gravitational waves, but some of the collisions produced black holes larger than we'd expect based on stellar evolution models. How did such large black holes form? Let me tell you about the mysteries of dark matter and dark energy more comprehensively. Dark matter comprises 85% of all matter in the universe. Yet we can't detect it. We can only infer its presence from its gravitational effects. We've searched for dark matter particles for decades. Nothing. We've proposed candidates, weakly interacting massive particles, axions, primordial black holes, sterile neutrinos. Yet none have been detected conclusively. Some physicists propose that dark matter doesn't exist. Maybe gravity works differently at large scales. Maybe Einstein's theory of gravity is wrong. But observations favor dark matter. Galaxy clusters behave as if dark matter exists. The pattern of structures in the universe matches predictions if dark matter exists. Modified gravity theories have been tested and largely rejected. So we're left with a mystery. The universe is full of invisible matter that makes up most of its mass. But we don't know what it is. Dark energy is even more mysterious. It makes up 68% of the universe's total energy. It's causing cosmic expansion to accelerate. Yet we know almost nothing about it. The cosmological constant is our best guess. But calculating what it should be from first principles gives a value that's 10 to the power of 120 too large. That's the biggest error in physics. Let me tell you about exoplanet mysteries. We've discovered thousands of exoplanets. They should follow predictable patterns based on planet formation theory. But they don't. We have hot Jupiters, massive gas giants orbiting close to their stars. Our models say they should form far away and then migrate inward. But do all of them? We're not sure. We have super-Earths and mini-Neptunes, planet types that don't exist in our solar system. They're common around other stars, but our formation models don't easily explain them. We have planets in highly eccentric orbits that should have been ejected, yet they persist. Each exoplanet discovery reveals another way the universe violates our expectations about how planets form and evolve. Let me tell you about stellar evolution mysteries. Stars are born, live, and die. We understand the basic process, but details remain mysterious. How do massive stars form? Radiation pressure should prevent their growth, yet they exist. How do binary stars with extreme mass ratios form? They shouldn't be stable, yet we observe them. How do stars in the galactic bulge differ from stars in the disk? Why do different populations have different properties? Our models explain the outlines but miss the details. The universe keeps surprising us. Let me tell you about the mysteries of supernovae. Type 1. A supernovae should all have similar brightness if our models are right. But they don't. Some are brighter, some are dimmer. We've developed empirical methods to standardize them, but we don't understand why they vary. If our standardization is wrong, our cosmic distance scale is wrong. The expansion rate of the universe is wrong. Dark energy is wrong. Type 2 supernovae explode when massive stars collapse. But our computer simulations struggle to produce explosions with observed energies. Something about the physics isn't right. Let me tell you about neutron star mysteries. Neutron stars are the densest objects we can observe directly. A teaspoon would weigh billions of tons. Yet we don't fully understand their structure. We don't know the exact composition. We don't understand the phases of matter that exist in their cores. Some neutron stars are pulsars. Some are magnetars. Some are in binary systems producing X-rays. Each type presents mysteries. Let me tell you about cosmic ray mysteries at higher energy. The highest energy cosmic rays have energies we can barely comprehend. They're traveling at nearly the speed of light with kinetic energy from accelerating to that speed. Yet we don't know their sources. The known accelerators, supernovae, and pulsars shouldn't produce cosmic rays this energetic. Something unknown is accelerating particles to impossible speeds. Something unknown is filling the universe with high-energy cosmic rays we can't explain. Let me tell you about the mysteries of large-scale structure. The universe isn't uniform. Galaxies form structures, filaments of galaxies, walls, voids. This is more dramatic than our models predict. The universe should be more uniform, but it's not. It has extreme structure. How did this structure form? What processes led to such dramatic organization? We have ideas but not complete understanding. Let me tell you about the mysteries of cosmic distance and expansion. Measuring distances to distant objects is foundational for cosmology. We use supernovae as standard candles, but supernova brightness varies. We standardize them empirically. But what if our standardization is wrong? Different distance measurement methods give slightly different results. The Hubble tension, a discrepancy between different expansion rate measurements, might indicate a problem with one or more methods. Or it might indicate that the universe is more complex than our models. Maybe the expansion rate is changing. Maybe space has properties we don't understand. Let me explore even more mysteries that are shaping modern astronomy and physics. The missing satellite problem is a genuine discrepancy between theory and observation. Our models of galaxy formation predict that the Milky Way should have hundreds of dwarf satellite galaxies orbiting it, but we observe only a few dozen. Where are the missing satellites? Did they not form? Did they get destroyed? Are they hiding, too dim for us to detect? This discrepancy suggests something is wrong with either our galaxy formation models or our understanding of dark matter dynamics. It's been called one of the biggest problems in cosmology, a concrete prediction that doesn't match observation. Every new observation of satellite galaxies or every refinement to the models represents a step toward understanding what's really happening. Let me tell you about the cosmic microwave background anomalies. The cosmic microwave background is radiation left over from the Big Bang. It's remarkably uniform, almost perfectly uniform, but it has anomalies. There's a cold spot, a region that's colder than the surrounding areas. There are asymmetries that suggest the universe might not be isotropic. Some of these anomalies might be statistical flukes. When you measure something with trillions of data points, some patterns will look unusual just by chance, but others might be real. Some might point to new physics. We don't know, and that uncertainty is genuinely unsettling. One of our best windows into the early universe might be showing us hints of physics we haven't discovered. Let me tell you about the rotation of the sun. The sun's equator rotates faster than its poles. The equator completes a rotation in 25 days. The poles take 35 days. This differential rotation is expected because the sun is a fluid body with magnetic fields. But the exact mechanism that creates this pattern, partially mysterious. The solar dynamo, the process that generates the sun's magnetic field, remains incompletely understood. This matters because the solar magnetic field drives solar flares and coronal mass ejections that affect Earth's space environment. Let me tell you about the mysteries of pulsars in binary systems. Some pulsars orbit companion stars. This creates an incredible laboratory for testing physics. We have binary pulsars where both stars are pulsars. We can measure their orbital parameters with incredible precision. We can test general relativity. We can look for deviations from Einstein's predictions. So far, general relativity holds up, but the precision measurements reveal complexities. Precession, orbital decay. Effects we understand theoretically, but that become fascinating when measured precisely. Let me tell you about the mysteries of rogue black holes. We've realized that black holes might be ejected from galaxy centers during mergers. Two supermassive black holes merging can produce gravitational waves that are asymmetric, creating a recoil that kicks the merged black hole out of the galaxy. These rogue black holes wander through intergalactic space. We might be able to detect them through their effects on surrounding gas or through gravitational lensing. But how common are they? How much do they affect galactic evolution? We're still figuring this out. Let me tell you about the mysteries of fast X-ray transients. These are X-ray binary systems that undergo rapid brightenings. One moment they're dim, the next moment they're bright. The transition happens in hours or even minutes. What causes these sudden transitions? Is it material streaming onto the neutron star suddenly? Is it a change in accretion geometry? We have theories, but the details remain mysterious. Let me tell you about the mysteries of gravitational wave events. We've detected dozens of gravitational wave events now. Merging black holes, colliding neutron stars. Each event provides information about the universe. But some events are unexpected, black hole masses that shouldn't exist based on stellar evolution. Binary systems with properties we didn't predict. Gravitational wave astronomy is revealing that stellar evolution is more complex than we thought. There are formation channels for unusual systems that we're only beginning to understand. Let me tell you about the mysteries of pulsar glitches. Most pulsars maintain incredibly regular rotation, but occasionally they suddenly speed up. They glitch. A glitch involves a sudden increase in rotational frequency. The pulsar is rotating at one rate, then suddenly rotates faster. The rotation gradually returns to the expected rate over hours to months. What causes glitches? Some models involve starquakes, sudden rearrangements of the neutron star's crust. Others involve decoupling between the crust and the superfluid interior. We're not sure which is correct. Each glitch is an opportunity to study neutron star physics. But we still don't fully understand these events. Let me tell you about the mysteries of gamma ray bursts. These are the most energetic explosions in the universe. A single gamma ray burst can release more energy than our sun will release in its entire life. We've identified some progenitors: massive star core collapses, neutron star mergers. But some gamma ray bursts don't have obvious progenitors. Their origins remain mysterious. Let me tell you about the mysteries of tidal disruption events. When a star gets too close to a supermassive black hole, the black hole's gravity tears it apart. The star is shredded by tidal forces. This creates an observable event, a tidal disruption event. Gas falls toward the black hole, heats up, radiates. We can observe this radiation, but the exact physics remains mysterious. How does the disrupted material distribute? What determines the radiation we observe? How close does the star need to get? These questions matter because tidal disruption events give us information about black holes and the centers of galaxies. Let me tell you about the mysteries of the early universe. The Big Bang created the universe about 13.8 billion years ago. But we don't fully understand what happened in the first moments. Inflation, a period of incredibly rapid expansion, is part of standard cosmology. But we don't understand what caused it. What is the inflaton field? What physical process drives inflation? Some observations give us hints. The cosmic microwave background has properties that match inflation predictions. But we need more data to confirm or refute specific inflation models. Let me tell you about the mysteries of cosmic reionization. In the early universe, hydrogen was neutral. Then galaxies formed and their light ionized the hydrogen. This happened gradually over hundreds of millions of years, but we don't fully understand this process. Which sources ionized the universe? Galaxies? Quasars? The relative contribution remains unclear. Let me tell you about the mysteries of ultra-high redshift galaxies. We're discovering galaxies at incredibly high redshifts, objects from the very early universe. But some of these galaxies are too large, too mature. They shouldn't have had time to develop into such massive systems so soon after the Big Bang. This suggests either that our galaxy formation models are wrong or that we're seeing exceptional objects. Either way, it's a puzzle. Let me tell you about the mysteries of quasar absorption systems. When light from a distant quasar passes through intergalactic gas, the gas absorbs some wavelengths. By studying these absorption lines, we can learn about the intergalactic medium. We can study how it evolved. We can probe regions we couldn't otherwise observe. But the measurements reveal complexity. The gas isn't uniformly distributed, it has structure, filaments, voids, features we're still trying to understand. Let me tell you about the mysteries of the Lie Alpha forest. This is a name for the pattern of absorption lines in quasar spectra created by neutral hydrogen in the intergalactic medium. The Lie Alpha forest tells us about the universe's structure on small scales, but interpreting it requires understanding the intergalactic medium's properties. How is the gas distributed? What is its temperature, its density? We have models, but the models must be tested against observations, and observations keep revealing complexities. Let me tell you about the mysteries of cosmic string detection. Cosmic strings are theoretical objects, one-dimensional defects in spacetime predicted by some theories. If they exist, they would have observable effects: gravitational lensing, gravitational waves, other signatures. But we haven't detected them. Do they exist? Are they too rare to detect? Are they fictitious? We don't know. Let me tell you about the mysteries of primordial black holes. Maybe black holes formed in the early universe from density fluctuations rather than from stellar collapse. Primordial black holes might exist in abundance. They might compose dark matter. They might have been detected through gravitational wave signatures from mergers, but we're not sure. The existence of primordial black holes remains speculative but possible. Let me tell you about the mysteries of asteroids and comets. We think we understand their origins. Asteroids are remnants of planetary formation. Comets are icy bodies from the outer solar system, but their actual compositions surprise us. Meteorites from asteroids have properties we don't always expect. Comets have varied compositions and behaviors. Each new asteroid and comet observation reveals another complexity. Let me tell you about the mysteries of the zodiacal light. When the sun has set and darkness falls, if you look toward where the sun set, you might see a faint glow. This is the zodiacal light, sunlight scattered by dust in the plane of the solar system. But the dust distribution that creates this light has mysteries. Where does the dust come from? How is it maintained? How is it distributed? Partially mysterious. Let me tell you about the mysteries of planetary auroras on other worlds. Earth has auroras, beautiful lights caused by solar wind interactions. But other planets have auroras too. Jupiter's auroras are more energetic than Earth's. They're brighter relative to the planet's size. Saturn has auroras. Uranus has unusual auroras. But we don't fully understand the mechanisms. Why are some planets' auroras so different from Earth's? Let me tell you about the mysteries of stellar winds. Stars emit winds, streams of particles flowing outward from their surfaces. The sun's solar wind is mild, but massive stars emit powerful stellar winds. Some stellar winds are so powerful they're comparable to explosions. We don't fully understand these winds. What determines their properties? Why do different stars have such different wind strengths? Let me tell you about the mysteries of stellar rotation. Different stars rotate at different rates, some slowly, some very fast. But the distribution of stellar rotations presents mysteries. Why do some stars rotate so fast? How do they maintain such rapid rotation? The answers relate to stellar evolution and magnetic fields, areas where mysteries still abound. Let me explore the deepest mysteries, the ones that touch on fundamental physics and the nature of reality itself. Let me tell you about the mysteries of space-time at its smallest scales. General relativity and quantum mechanics don't play well together. At the scale of black hole singularities in the early Big Bang, both theories apply, but they give contradictory predictions. This means we're missing a theory. We need quantum gravity, a theory that unifies quantum mechanics and general relativity. But we don't have one yet. String theory is a candidate. Loop quantum gravity is another. But neither is proven. At the Planck scale, about 10 to the power of minus 35 meters, space-time becomes quantum. It's not smooth, it's foamy, it fluctuates, but we don't understand these fluctuations. We don't know what happens there. Mysteries at the Planck scale could explain dark matter, could explain dark energy, could explain fundamental aspects of reality we don't understand. Let me tell you about the mysteries of the initial conditions of the universe. The Big Bang set initial conditions, but we don't know what determined those conditions. Why did the Big Bang happen? Why did it have the properties it did? These are profound questions without answers. Some physicists propose that the universe tunneled into existence from nothing, but this requires interpreting quantum mechanics in ways that aren't fully established. Others propose cyclical models where the universe goes through infinite cycles. But these models are speculative. We're left with mysteries about the universe's deepest origins. Let me tell you about the mysteries of consciousness and quantum mechanics. Some interpretations of quantum mechanics suggest that consciousness plays a role in collapsing wave functions. If true, consciousness would be fundamental to physics. The observer wouldn't just measure reality, they would create it through observation. This is controversial. Most physicists reject this interpretation, but the relationship between observation and quantum mechanics remains mysterious. Let me tell you about the mysteries of life's origin. We don't know how life began. Abiogenesis, the origin of life from non-living chemistry, remains one of the biggest unsolved problems in science. We have theories: autocatalytic networks, the RNA world, clay mineral templates. But we don't know which is correct. We don't even know if life originated once or multiple times. If life can originate readily from chemistry, the universe might be full of life. If life is incredibly rare, so we might be nearly alone. This depends on understanding abiogenesis. Let me tell you about the mysteries of consciousness itself. Consciousness is the most immediate experience we have, yet it's mysterious in ways that are hard to articulate. How does the brain generate consciousness? We know it involves electrical activity and chemical reactions, but how do these physical processes create the subjective experience of being? This is the hard problem of consciousness. No one knows how to solve it. Some think it might require new physics. Others think it's solvable within known physics, but we haven't figured it out yet. If consciousness requires new physics, then neuroscience is connected to fundamental physics in unexpected ways. Let me tell you about the mysteries of free will. Do we have free will, or is everything determined by physics? Quantum mechanics introduces randomness, but randomness isn't the same as free will. A random process isn't a freely chosen action. This mystery touches on philosophy and physics intertwined. We don't know if free will is compatible with physics as we understand it. Let me tell you about the mysteries of the arrow of time. Time flows one direction, past to future, but the fundamental laws of physics work equally well in both directions. Why does time have a direction? Entropy provides an answer. Entropy increases toward the future. But this seems like a tautology. We define the future as the direction entropy increases. So why does entropy increase? The answer involves the initial conditions of the universe. The universe started in a low entropy state. Entropy has been increasing since. But why was the initial state low entropy? This remains mysterious. Let me tell you about the mysteries of vacuum decay. The vacuum, empty space, has an energy density. But maybe our vacuum isn't the lowest energy state. Maybe a lower energy vacuum exists. If so, empty space could spontaneously transition to the lower energy state. This would create a bubble of new space expanding at light speed. Everything inside would be destroyed. The process is called vacuum decay or false vacuum decay. We don't know if it's happening. We don't know how likely it is, but the possibility is disturbing. It means reality could disappear. Let me tell you about the mysteries of supersymmetry. Many physicists believe that nature has a hidden symmetry called supersymmetry. It would pair every particle with a superpartner. Electrons would have superpartners. Photons would have superpartners. Gravity would have superpartners. But no superpartners have been detected despite extensive searches. Either supersymmetry doesn't exist, or the superpartners are more massive than we expected, or they're hidden in ways we don't understand. Let me tell you about the mysteries of extra dimensions. String theory predicts that space has more than 3 dimensions. There might be 6 or 7 extra dimensions curled up at the Planck scale. But we've never detected these extra dimensions. We don't know if they exist. Detecting them would require energies far beyond what we can achieve with current technology. Yet if extra dimensions exist, they could explain mysteries like dark matter, dark energy, and the hierarchy problem. They could unify physics in unexpected ways. Let me tell you about the mysteries of quantum entanglement. When two particles are entangled, their states are correlated. Measuring one immediately affects the other, even across vast distances. This seems to violate locality, the principle that effects can't propagate faster than light. But quantum mechanics allows this. Somehow, measurements made instantaneously affect distant entangled particles. How is this possible? How does information travel faster than light? We don't know. It remains one of quantum mechanics' deepest mysteries. Let me tell you about the mysteries of quantum tunneling. In quantum mechanics, particles can penetrate barriers they shouldn't be able to cross classically. An electron can tunnel through a wall even though it doesn't have enough energy to climb over it. The probability is low, but it's non-zero. Given enough time, it will tunnel through. This is how nuclear fusion happens in stars. Protons tunnel through the barrier that should keep them apart. Without tunneling, stars couldn't fuse hydrogen into helium. The universe wouldn't work. But why can quantum particles do this? What's the mechanism? We have mathematical descriptions, but we don't fully understand the underlying physics. Let me tell you about the mysteries of antimatter. When the Big Bang created the universe, it created equal amounts of matter and antimatter. But antimatter annihilates when it meets matter. So why is there any matter left? Why didn't it all annihilate? There must be an asymmetry. Some process that favored matter over antimatter. We found small asymmetries in certain particle decays, but they're not large enough to explain the matter-antimatter imbalance. There's a mystery here. We don't understand why the universe contains matter instead of being empty. Let me tell you about the mysteries of neutrinos. Neutrinos are ghost-like particles that barely interact with matter. Trillions pass through your body every second without interacting. But we don't fully understand neutrinos. They have mass, but it's incredibly small. They oscillate between flavors. They're produced in nuclear reactions and in the sun. But many aspects of neutrino physics remain mysterious. What determines their masses? What's their role in the universe? Are they their own antiparticles? Let me tell you about the mysteries of the cosmological constant problem. We calculated what the vacuum energy density should be. We got a number. Then we measured the vacuum energy density experimentally. It was 10 to the power of 120 times smaller. This is the worst prediction in physics. The worst by an absurd margin. Either our calculation is fundamentally wrong, or our measurement is wrong, or we're measuring different things and not realizing it. No one knows. This remains one of the deepest mysteries in physics. Let me tell you about the mysteries of fine-tuning. The universe has many physical constants: the strength of fundamental forces, particle masses, coupling constants. If these constants were slightly different, the universe would be radically different. Stars wouldn't form, atoms might not form, life couldn't exist. Yet these constants have exactly the values needed for complexity and life. Is this an incredible coincidence? Or does it hint at something deeper? Some physicists propose the multiverse, infinite universes with different constants. In most universes, life doesn't exist. We observe our universe because we exist in it, but this can't be tested. The mystery remains. We don't know why the constants have their values. We don't know if fine-tuning is coincidence or hint. Let me tell you about the mysteries of the holographic principle. This proposes that a three-dimensional volume of space can be described by information on its two-dimensional boundary. It sounds absurd, yet it emerges from quantum gravity research. It suggests that our three-dimensional reality might be a projection of information from a lower dimensional surface. If true, it would revolutionize our understanding of space and reality. But we don't know if it's correct. It remains speculative. These mysteries, consciousness, free will, time's arrow, vacuum decay, extra dimensions, quantum mechanics foundations, fine-tuning, and the holographic principle, represent the deepest unknowns in physics. They touch on the nature of reality itself. They connect physics to philosophy. They suggest that we're missing fundamental pieces of understanding. Each mystery is an invitation to think deeply, to question assumptions, to imagine possibilities. The universe is far stranger than we imagined, far more mysterious, far more wonderful. Let me talk about what these mysteries mean for the future of astronomy and physics, because these unsolved questions point toward where the next breakthroughs will happen. Fast radio bursts are already revealing secrets. Each new detection teaches us something. We're building a catalog of FRB properties. We're looking for patterns. Some repeat, some don't. Some have afterglows, some don't. Each characteristic constrains the possible progenitors. Within a decade, we might understand fast radio bursts. We might identify the mechanism. It could revolutionize our understanding of neutron stars, black holes, or exotic physics. The search for dark matter continues with new technologies. Experiments are becoming more sensitive. If dark matter consists of particles we haven't discovered, advanced detectors might find them. We might finally answer the question, what is 85% of matter? The search for dark energy might reveal whether the universe's expansion is truly accelerating or whether our observations have systematic errors. Different measurements might converge on a single answer, or they might reveal that the universe is more complex than we thought. Gravitational wave astronomy is in its infancy. We've detected dozens of events, but there are undoubtedly many more waiting to be discovered. As detector sensitivity improves, we'll observe mergers we haven't seen yet, new types of objects, new physics. Exoplanet science is accelerating. New missions, like the James Webb Space Telescope and future telescopes, will image exoplanets directly. They'll analyze their atmospheres. They'll search for biosignatures. We might detect life on another world in your lifetime. The study of the early universe will improve with next-generation surveys. We'll map the cosmic web in unprecedented detail. We'll observe ultra-high redshift galaxies with new precision. We might solve the problems of cosmic inflation, reionization, and early structure formation. Neutrino physics will advance with next-generation experiments. We might determine whether neutrinos are their own antiparticles. We might measure their masses precisely. Neutrinos might help us understand dark matter or other mysteries. But here's what excites me most. We're at the frontier of understanding. We know enough to recognize our ignorance. We have tools powerful enough to probe mysteries. We have technologies that would have seemed like magic a century ago. Sasur, mysteries of space aren't obstacles, they're opportunities. Each unsolved problem is a door to discovery. Each discrepancy between theory and observation is a signpost pointing toward truth. Throughout history, scientific revolutions have come from mysteries. Newton's laws emerged from the mystery of planetary motion. Einstein's relativity emerged from the mysteries of light and gravity. Quantum mechanics emerged from the mysteries of atomic structure. Today we have mysteries that might lead to equally profound revolutions. The nature of consciousness, the arrow of time, the origin of the universe, the nature of space and time themselves. These aren't mystical or unknowable questions. They're scientific questions. They're hard, but they're solvable. Future scientists will understand things we can barely conceive. Maybe you'll be one of those scientists. Maybe you'll be the person who solves the fast radio burst mystery. Maybe you'll discover what dark matter is. Maybe you'll find signatures of life on another world. The universe has been revealing its secrets slowly. Each generation understands more than the last. But we're nowhere near complete understanding. Most mysteries remain. Most of the universe is still unknown. This should fill you with wonder. We live in an age of discovery. We have questions that demand answers. We have the tools to search for those answers. The next revolution in physics might come from understanding a phenomenon we've recently discovered. The next great discovery in astronomy might come from solving one of these mysteries. The universe is waiting. It has hidden the secrets of dark matter for billions of years. It has been hiding fast radio bursts until we built sensitive enough detectors. It has been concealing the nature of consciousness in the complexity of the brain. But each secret is discoverable. Each mystery has a solution. Each question has an answer waiting to be found. That's what makes physics and astronomy so exciting. We're not just studying the universe, we're actively uncovering its secrets. Every observation reveals something we didn't know. Every measurement constrains the possibilities. The mysteries I've described, from fast radio bursts to consciousness, from dark matter to the nature of time, these are the frontier of human knowledge. This is where understanding deepens. This is where revolutions happen. You live in the age when these mysteries are being actively investigated. You live when we have the technology to search for answers. You live when solutions might emerge. The universe is beautiful because it's mysterious, because it still holds secrets, because understanding it is the great adventure of our time. I'm grateful for that. Grateful for mysteries that call us to think deeply. Grateful for questions that demand answers. Grateful for a universe complex enough to keep surprising us. Let me go even deeper into some of these mysteries because they deserve exploration from multiple angles. Consider fast radio bursts again. When we first discovered them, astronomers were skeptical. Skepticism is healthy in science. Extraordinary claims require extraordinary evidence. But the evidence accumulated, detection after detection, different telescopes, different teams, all confirming the same phenomenon. Now we take fast radio bursts seriously. We have entire research programs dedicated to finding them. Telescopes worldwide scan the skies for these brief signals. We're discovering new ones regularly, some with properties that challenge our models even more. What excites me about FRBs is that they're humbling. We've mapped billions of galaxies. We understand stellar evolution. We can predict planetary positions years in advance. Yet we discovered an entire class of astronomical phenomena we couldn't identify. This should give us perspective. The universe is stranger than our current theories accommodate. There are phenomena out there we haven't discovered yet, mysteries waiting for instruments sensitive enough to reveal them. Consider dark matter again. We've searched for it intensively. We've built ever more sensitive detectors. We've looked at the universe in radio, infrared, X ray, and gamma ray wavelengths. We've created computer simulations. We've developed theoretical models. Yet dark matter eludes us. This isn't failure, this is progress. Each failed search eliminates possibilities. Each theoretical development narrows the options. Eventually, we'll understand dark matter, but the path involves hypothesis, testing, and rejection of inadequate explanations. The process is slow. It requires patience, but it's how science actually works. Not dramatic eureka moments, but careful accumulation of evidence. Consider gravitational waves. They were predicted over a century ago, but we couldn't detect them. The signals are incredibly faint. The strain in space-time from even massive distant events is minuscule. Yet we built LIGO, Laser Interferometer Gravitational Wave Observatory. Two detectors miles apart. So sensitive they can measure changes in length smaller than a proton. And in 2015, they detected gravitational waves. Since then, we've detected dozens of events. We've opened an entirely new way of observing the universe. We're seeing phenomena, black hole and neutron star mergers, we couldn't see before. This is what science does. It creates new tools. It opens new windows. It reveals phenomena previously hidden. Consider exoplanets. A few decades ago, we didn't know any planets existed beyond our solar system. Now we've discovered thousands. We have catalogs. We study their properties. We ask, which might harbor life? The pace of discovery is accelerating. New survey methods, new telescopes, new detection techniques. We're finding exoplanets in places we thought impossible. Exoplanets that violate our models. This is exciting. Each new exoplanet teaches us about planetary formation. Each oddball system hints at physics we don't fully understand. Consider the mysteries of stellar evolution. Stars are born. They live. They die. The process takes billions of years for stars like our Sun. We understand the basic outlines, but details remain mysterious. How exactly does a star form? We have computer simulations, but they require assumptions about initial conditions. Tweak the assumptions slightly and the outcomes change dramatically. Are our simulations capturing reality, or are we getting outcomes by chance? How do massive stars stabilize? Radiation pressure should prevent their growth, yet they form and endure. There's physics we're missing, some process that lets massive stars form despite theoretical obstacles. When stars die, explosions happen. Supernovae, gamma ray bursts, neutron star mergers. These are the most energetic events in the universe, yet we don't understand their details. Our computer simulations struggle to reproduce observed explosions with observed energies. Something in our physics is incomplete. Some mechanism we haven't identified. Some process we don't fully account for. These mysteries in stellar physics connect to cosmology. Supernovae are used as distance markers. If we don't understand supernovae, our cosmic distance scale might be wrong. Our measurements of cosmic expansion might be wrong. Everything built on that foundation becomes uncertain. Consider the mysteries of planetary atmospheres. Some exoplanets should lose their atmospheres. Stellar radiation should strip them away. yet they retain atmospheres. Some planets shouldn't have atmospheres at all, yet observations suggest they do. Their atmospheres persist despite theoretical predictions they should evaporate. This suggests our models of atmospheric escape are incomplete. We're missing something about how atmospheres interact with radiation and stellar wind. But this matters. The existence of atmospheres affects habitability. If our models are wrong, our estimates of where life could exist might be wrong. Consider the mysteries of planetary cores. Planets have dense cores. Earth's core is mostly iron. But how did the core form? Did iron sink to the center during planet formation? Over how long? Through what mechanism? Our models predict that planetary cores should take longer to form than planets apparently take to form. There's a timing problem. Either planets form faster than we think, or planetary cores form through processes we haven't identified. Again, a mystery that seems minor, how planetary cores form, connects to fundamental questions. How do planets form? How long does it take? What determines planetary properties? Consider the mysteries of planetary magnetism. Some planets have strong magnetic fields, others don't. Why? Jupiter has a powerful magnetic field. Venus has almost no magnetic field. Why would two similar-sized planets have such different magnetic field strengths? The answer involves planetary interiors. It involves the composition and structure of planets' cores and mantles. It involves the physics of magnetohydrodynamics in planetary interiors. We don't fully understand how planetary magnetic fields generate and maintain themselves, but planetary magnetic fields affect habitability. They protect planets from stellar wind and cosmic rays. If a planet loses its magnetic field, the upper atmosphere can be stripped away. Habitability changes. So understanding planetary magnetism connects to understanding habitability, which connects to understanding where life might exist. Each mystery connects to others. Mysteries of stellar evolution connect to mysteries of planetary formation. Mysteries of planetary atmospheres connect to mysteries of habitability. Mysteries of dark matter connect to mysteries of galaxy formation. Science isn't a collection of isolated questions. It's an interconnected web. Understanding one piece often illuminates others. That's what makes science so beautiful. Problems are related. Solutions resonate across domains. A breakthrough in one area creates breakthroughs in others. The mysteries I've described aren't dead ends. They're pathways. They're invitations to think more deeply. They're hints that greater understanding awaits. Let me talk about how we approach unsolved mysteries in modern astronomy, because the method matters as much as the mysteries themselves. Science is a process of asking questions and testing answers. But mysteries require a particular approach. You can't test what you don't understand. You can't measure what you can't detect. For fast radio bursts, we started with raw data, signals arriving from space. We had to first confirm they were real and not instrumental artifacts. Then we had to characterize them, measure their frequencies, their timing, their energies. Only then could we begin proposing mechanisms. For dark matter, we measure its gravitational effects, but this indirect measurement limits what we can learn. We know dark matter exists. We know roughly how much. We know where it's distributed, but we don't know what it is. So we search directly for particles that might comprise dark matter. We build increasingly sensitive detectors. We analyze their results carefully. Absence of detection is still useful information. It eliminates possibilities. For exoplanets, we first detected them by observing their effects on host stars. A planet's gravity makes the star wobble or creates a slight dimming as the planet passes in front. From these indirect measurements, we inferred planets existed. Now we're observing them more directly, imaging them, analyzing their light, studying their atmospheres. The approach evolves as technology improves. For gravitational waves, we had to build a detector sensitive enough to measure the infinitesimal distortions of spacetime. We had to develop data analysis techniques to identify real signals in noise. We had to understand the sources theoretically so we'd recognize what we were seeing. These methodological challenges are part of the scientific adventure. Solving a mystery requires not just theoretical insight, but technical innovation. Let me tell you about one specific mystery that illustrates how science works. The lithium problem, which I mentioned earlier, but deserves deeper exploration. We measure lithium in old stars. The amount is about 1,000 times less than Big Bang nucleosynthesis predicts. This discrepancy, the lithium problem, has troubled astronomers for decades. First, scientists confirmed the measurements. Multiple teams, different telescopes, different methods, all confirmed that lithium abundance in old stars is too low. Then scientists proposed explanations. Maybe stars are destroying lithium. Maybe mixing in stellar interiors is more efficient than we thought. Maybe additional nuclear processes are occurring, so they built models. They ran simulations. They compared predictions to observations. Some ideas were rejected, some seemed promising, but none completely resolved the discrepancy. Maybe the problem lies not with stars, but with our understanding of the Big Bang. Maybe nucleosynthesis produces different abundances than we calculate. Maybe something about the early universe, conditions, processes, or physics is different from our models. This led to refinements in Big Bang nucleosynthesis theory, which led to new predictions, which were compared to observation. Decades later, the lithium problem remains partially unsolved, but the investigation has deepened our understanding of stellar physics, nuclear burning, and Big Bang nucleosynthesis. Even partial solutions are valuable. Yikes. This is how science works. A mystery stimulates investigation. Investigation reveals unexpected complexities. Deeper understanding emerges. Even if the original question isn't fully answered, knowledge expands. Let me talk about future prospects for solving the mysteries I've described. Fast radio bursts. Within the next decade, surveys will likely detect thousands of FRBs. With a large statistical sample, patterns will emerge. The repeating sources will be studied intensively. Eventually, we'll identify the mechanism. I'd guess within 10 years. Dark matter. New detection experiments will come online. If dark matter particles exist and interact as we expect, we'll detect them. If not, theories will be revised. We'll learn something crucial either way. Perhaps within 20 years. Dark energy. Better measurements of cosmic expansion will reduce uncertainties. Different measurement methods will hopefully converge on consistent results. If they don't, it will hint at complexity we haven't recognized. Progress will come. Timescale uncertain. Exoplanet atmospheres. New telescopes will analyze atmospheres of increasing numbers of exoplanets. We'll characterize atmospheric compositions, temperatures, and dynamics. We'll search for biosignatures. We'll identify habitable worlds. This will accelerate over the next decade. Gravitational waves, detector sensitivity will improve. We'll observe mergers with unprecedented precision. We'll detect new types of events. We'll learn about the end states of stellar evolution and the properties of neutron stars and black holes. This will continue advancing steadily. Black hole physics. As we observe black holes more closely through gravitational lensing, X-ray emission, and gravitational waves, we'll learn about their properties, formation, and interactions. We might test general relativity in strong field regimes. Revolutionary insights await. The early universe. Next generation telescopes will observe increasingly distant and younger galaxies. We'll constrain inflation models. We'll understand reionization. We'll possibly detect the first stars and galaxies. The cosmic history will become clearer. Stellar evolution. Detailed observations of stars in different environments and ages will reveal how stellar properties change. Asteroseismology, using stellar oscillations to probe internal structure, will improve. We'll understand stellar interiors better. Planetary formation. Observations of protoplanetary disks with next-generation telescopes. Exoplanets. Now we've found thousands. Just 30 years ago, we weren't sure dark matter existed. Now we know it comprises most of the matter in the universe. What will we discover in the next 30 years? What mysteries will we solve? What phenomena will we reveal? I believe we'll discover things that will seem as profound and transformative as heliocentrism or evolution. Discoveries that will reshape how we understand reality. Some of you will contribute to those discoveries. Some of you might make the breakthrough observations. Some might develop the theories. Some might build the instruments. The universe needs explorers. It needs people curious enough to ask deep questions, people thoughtful enough to recognize mysteries, people determined enough to solve them. This is where we stand, facing mysteries, equipped with tools, driven by curiosity. What could be more exciting? Let me tell you what I find most striking about the unsolved mysteries of space. It's not any individual mystery. It's that together they point toward something. We don't understand dark matter. We don't understand dark energy. We don't understand consciousness. We don't understand time's arrow. We don't fully understand how planets form or how life originated. These aren't random gaps in knowledge. They cluster around fundamental aspects of reality. What is matter? What is energy? What is consciousness? What is time? What is life? These are the deepest questions philosophy and science can ask, and we're actively investigating them. Maybe solving one will illuminate the others. Maybe dark matter relates to consciousness in ways we can't imagine. Maybe understanding time connects to understanding consciousness. Maybe life's origin relates to quantum mechanics and the nature of information. I don't know. But the interconnections are tantalizing. When science makes revolutions, they often come from unexpected directions. Darwin's evolution didn't start as a study of evolution. He was observing finches' beaks. Planck's quantum mechanics emerged from studying black body radiation. Einstein's relativity emerged from studying light. The next revolution might emerge from studying fast radio bursts, or from dark matter research, or from unexpected correlations between unrelated mysteries. This is what keeps me awake at night. Not anxiety, but excitement. What might we discover? What paradigm shifts are waiting? The universe is vast beyond comprehension. Billions of galaxies, trillions of stars, more planets than stars, and we understand only a fraction of it. Yet each fraction reveals complexity. Each system we study, from stars to galaxies to the cosmic web, has unexpected properties, surprises, mysteries. This vastness, this complexity, this capacity to surprise, it's beautiful. It means the universe is rich with meaning. rich with phenomena to understand, rich with secrets waiting to be discovered. For thousands of years, humans wondered about the cosmos. We created myths and stories. We imagined the universe in ways that reflected our fears and hopes. Now we observe it scientifically. We measure it. We build theories. We test predictions. And still, mysteries abound. Still, the universe surprises us. I want to leave you with this thought. The mysteries of space are not distant abstractions. They're not removed from everyday life. They connect to who we are, how we think, and what we might become. The mystery of consciousness connects to what it means to be human, to think, feel, and experience, to be aware of the universe observing it. We don't fully understand how consciousness arises, but we know it's the most profound phenomenon we experience. The mystery of time connects to how we experience existence. We live in the present, remember the past, and anticipate the future. But what is time? Is it real? Does it flow? Or is it an illusion? Understanding time might transform how we understand existence itself. The mystery of life's origin connects to our deepest question. Are we alone? Do other minds exist in the universe? Life emerged from non-living chemistry on Earth. Is that common? Rare? Unique? If life is common, the universe might teem with consciousness. Billions of civilizations might exist. We might not be alone in any meaningful sense. If life is rare, we might be nearly unique, a precious anomaly in an otherwise sterile cosmos. The mysteries of planetary habitability determine where we might find life, which worlds might host biology, which planets might harbor consciousness. These questions transcend pure science. They touch our sense of purpose. They affect how we see ourselves in the cosmos. The mysteries of dark matter and dark energy connect to the universe's ultimate fate. If dark energy is permanent, the universe will expand forever. Space will grow infinitely vast. All matter will eventually decay. The universe will reach heat death, eternal, cold, empty. Understanding dark energy helps us understand the future of everything, not just physically, but philosophically. It shapes how we contemplate meaning and eternity. These mysteries matter because solving them might reveal fundamental truths. Truths about existence, consciousness, and reality. That's why I'm passionate about space exploration and scientific discovery. Not just for the practical applications, though there are many, but for the deeper understanding, for the perspective it gives us, for the humility it inspires. When you contemplate the universe's mysteries, you recognize the limits of human knowledge. You recognize how much we don't know. This humility is powerful. It opens minds. It inspires curiosity. It motivates deeper investigation. Some of you watching this will become scientists. You'll devote your careers to unraveling cosmic mysteries. You might make discoveries that reshape our understanding. You might solve problems that have perplexed humanity for centuries. Some of you might not become scientists, but will follow scientific developments closely. You'll appreciate the beauty of understanding. You'll marvel at the discoveries. You'll contribute by sharing knowledge, asking questions, supporting research. All of you can participate in the adventure. The universe invites all of us to wonder, to question, to seek understanding. The mysteries of space, from fast radio bursts to dark matter, from consciousness to time itself, are waiting. They're waiting for curious minds, for people willing to think deeply, for people determined to discover truth. The universe has given us the tools: telescopes that see billions of light years away, detectors sensitive to the faintest signals, computers that can model complex systems, theories that let us calculate cosmic evolution. We're equipped, we're motivated, we're ready. The next breakthrough could come tomorrow. It could come from an observation made by a teenager with a backyard telescope. It could come from a theoretical insight made by a student doodling in a notebook. The frontiers are open. The mysteries await their solvers. This is an extraordinary time to be alive, to be conscious, to be able to ponder the universe's deepest secrets. Appreciate that privilege. Use it wisely. Feed your curiosity. Ask deep questions. Wonder about the universe and your place in it. Let me spend a moment on why these mysteries matter, not just scientifically, but personally and philosophically. Science, at its core, is about extending the realm of human understanding. It's about transforming mysteries into knowledge, ignorance into insight, wonder into wisdom. Every civilization has faced the mysteries of the cosmos. Every culture has created stories to explain what they observed: gods, spirits, natural laws, mythology. Eventually, science emerged as a tool for understanding reality more accurately, not perfectly, not with absolute certainty, but science provides methods for testing ideas, for eliminating wrong answers, for getting closer to truth. The mysteries I've described, from fast radio bursts to consciousness, represent our current frontier. They're the boundaries of human knowledge. Beyond them lies territory unmapped. In earlier eras, that territory was vast. We didn't understand gravity. We didn't understand light. We didn't understand atoms. We barely understood life itself. Each era's mysteries were solved by each era's pioneers: Newton, Maxwell, Einstein, Darwin, Darwin, Planck, Dirac. Each solved mysteries that had perplexed their predecessors. Now it's our era. Now it's our turn. The mysteries facing us might seem harder. They are harder. We've already solved the easier problems. What remains are genuinely difficult questions. But that's what makes this era so exciting. We get to tackle the hardest questions. We get to work on the deepest mysteries. We get to potentially make revolutionary discoveries. The history of science shows that revolutions often come unexpectedly. Scientists work on one problem and discover something entirely different. Technologies developed for one purpose prove useful for another. LIGO was built to detect gravitational waves. It did. But in the process, we learned about black holes and neutron stars in unprecedented detail. The Hubble Space Telescope was designed to observe distant galaxies. It did that brilliantly. But it also observed exoplanet transits, contributed to measuring cosmic expansion, and discovered accelerating universe, dark energy. New discoveries often have unintended consequences. They illuminate unexpected areas. They solve problems we didn't know we had. So the mysteries are not just scientific questions, they're invitations. Invitations to think deeply, invitations to explore, invitations to potentially revolutionize our understanding. And here's what I find most beautiful: the mysteries are available to everyone. You don't need to work at a major research institution to contribute. Amateur astronomers discover supernova. Citizen scientists participate in data analysis. Students conduct research that advances fields. The frontiers of knowledge are not sealed off to professionals alone. They're open to anyone with curiosity, determination, and dedication. Some of you might discover the next fast radio burst source. Some might identify a pattern in dark matter data. Some might develop a theory that explains dark energy. Some might detect biosignatures on an exoplanet atmosphere. Or you might contribute in ways we can't predict. You might ask a question that opens new avenues. You might notice a pattern everyone else missed. You might think of an experiment no one has tried. The universe rewards curiosity. It rewards careful observation. It rewards thoughtful thinking. The mysteries await not just professional astronomers and physicists, they await anyone willing to engage with deep questions, to wonder, to investigate, to seek truth. That's what I love about astronomy and space science. The mysteries are genuinely open. The frontiers are real. The discoveries are waiting. The universe has been hiding its secrets from the earliest humans who looked up at the night sky. Generation after generation, we've peeled back the veil. We've revealed truth after truth, but we're far from complete understanding. Mysteries remain, profound mysteries, mysteries that might reshape our understanding of reality. This is an opportunity, a moment in human history when the great mysteries are accessible to investigation, when we have the tools to probe deep, when we have the knowledge base to ask intelligent questions. Don't waste this opportunity. Don't take for granted the privilege of living in an age when we can investigate cosmic mysteries. Before you go, let me emphasize something crucial about these mysteries. They're not esoteric or irrelevant. They're not abstract questions with no bearing on everyday life. Understanding the universe shapes how we understand ourselves, how we see our place in the cosmos, how we think about the future. When we solve the mystery of dark matter, we'll understand what the universe is made of, not just the visible 15%, but the hidden 85%. This knowledge changes our conception of reality. When we understand dark energy and cosmic expansion, we'll know the universe's ultimate fate. Is it endless expansion, eternal cold and emptiness, or something we haven't imagined? When we discover how life begins, we'll know if biology is common or rare in the cosmos. Are we unique? Part of an interconnected web of life across countless worlds? When we understand consciousness, we'll know something profound about ourselves, about the nature of awareness, about what makes us distinctly human. These aren't peripheral questions, they're central. They go to the heart of what it means to exist. The mysteries of space are intimately connected to mysteries of self. To understand the universe is to understand ourselves. This is why I'm passionate about space exploration, why I care deeply about solving these mysteries. It's not just intellectual curiosity, though there's plenty of that. It's existential. It matters. Every person watching this should feel that connection. The universe isn't something external to you. You're part of the universe. The atoms in your body came from stars, the calcium in your bones, the iron in your blood, the oxygen you breathe. You're made of stardust, literally. The heavy elements in your body were forged in stellar cores and scattered by supernovae. You're a product of cosmic evolution, a temporary arrangement of matter that became conscious. That's profound, that's beautiful, that's true. The mysteries we face about the universe's composition, its fate, its origins, are mysteries about you, about where you came from, where you're going, what the future holds. This is why unraveling these mysteries matters, not as abstract intellectual exercises, but as essential knowledge about reality. And this is why your participation matters. Science progresses through the efforts of many people, professional scientists, citizen scientists, enthusiasts, curious minds everywhere. If you're passionate about these questions, pursue that passion. Study science, conduct research, ask deep questions, push boundaries. If you're not a scientist but care about these mysteries, support scientific research, share knowledge, encourage others to wonder. If you're young and unsure of your path, consider that the frontiers of science might be calling you. The mysteries of space need solvers. The universe needs explorers. We stand at a remarkable moment in history. We have better tools than any previous civilization. We have better understanding. We have better technology. Yet the great mysteries remain. The adventure is far from over. The next chapter in humanity's cosmic understanding hasn't been written yet. It could be written by you. Let me conclude with a personal reflection on why these mysteries matter to me and why they should matter to you. I became fascinated with space as a child. I remember looking up at the night sky and realizing how vast it was, how many stars, how far away. It felt both humbling and terrifying and wonderful. As I learned more about astronomy, I discovered we didn't understand many things about the universe. We knew the outlines, but the details remained mysterious. Dark matter, dark energy, the origins of planets, the nature of consciousness. These mysteries drove me. They still do. Because unsolved mysteries represent possibilities. They represent territory unexplored. They represent the chance to discover truth that no one has articulated before. That's what science is, at its heart. It's the exploration of mystery, the transformation of ignorance into understanding. The mysteries I've described in this video, fast radio bursts, dark matter, dark energy, planetary formation, consciousness, the nature of time, these are our generation's frontier. They're the questions we get to answer, the problems we get to solve, the discoveries we get to make. This is a gift, a privilege, a responsibility. We live in an age when we have the tools to investigate cosmic mysteries, powerful telescopes, sensitive detectors, powerful computers, advanced theories, a global community of scientists collaborating worldwide. We also live in an age when those tools are becoming more accessible. More people can participate in scientific discovery. More people can contribute to solving mysteries. That's extraordinary. That's something to celebrate. It is true. The unknown is calling. The mysteries of space are inviting us to engage, to think deeply, to seek truth. Some of you will become astronomers or physicists. You'll devote your lives to these mysteries. You might make discoveries that reshape our understanding. Some of you might follow these fields passionately, but pursue different careers. You'll support scientific research. You'll encourage others. You'll share knowledge. All of you can participate in the adventure. All of you can wonder about the universe. All of you can ask deep questions. The mysteries don't discriminate. They invite everyone who's curious. So I encourage you to engage with these mysteries, to think about them, to research them, to support those who devote their lives to solving them. The universe is vast beyond comprehension. It contains more mystery than we could investigate in 1,000 lifetimes. Yet we continue. We push further. We dig deeper. And each generation makes progress. Each generation solves some mysteries and discovers new ones. It's an endless frontier, an infinite adventure. And you get to be part of it right now, in your lifetime. That's the most exciting thing I can tell you. The mysteries I've described today, from fast radio bursts to the nature of consciousness, represent the frontier of human knowledge. These are the questions that define our era in astronomy and physics. Each mystery is a door. Behind each door is the possibility of profound discovery. Each mystery invites the curious. Each invites the bold. Each invites anyone willing to think deeply about the cosmos. Throughout this video, I've tried to convey not just the mysteries themselves, but the wonder they inspire, the excitement they generate, the sense of being at the edge of understanding. This is what I love about science. It's a continuous process of discovery, of pushing boundaries, of transforming darkness into light. The universe has revealed many secrets over human history, yet the deepest questions remain. How did the universe begin? What is it made of? Are we alone? What is consciousness? What is time? These questions have captivated humans for millennia. Yet only now, in this modern era, do we have tools sophisticated enough to investigate them seriously. We stand at a remarkable moment, a moment where the great mysteries are within reach, where careful observation and rigorous thinking can pierce the darkness. The adventure continues. The mysteries await. The universe is full of secrets waiting to be discovered, and you could be the one to solve them. You could make the observation that changes everything. You could develop the theory that illuminates the darkness. You could discover the truth that transforms our understanding. Wow. That's the gift of living in this era. The privilege of having access to cosmic mysteries. The opportunity to contribute to humanity's understanding. I hope this video has inspired you. I hope it's opened your mind to the vastness of cosmic mystery. I hope it's kindled your curiosity. One last thought before you go. In the vastness of space, across billions of galaxies, on countless worlds, there might be other minds, other conscious beings pondering their own cosmic mysteries. They might be looking up at their night sky, wondering about the same fundamental questions. Where did the universe come from? What is it made of? Are we alone? What is consciousness? What happens when we die? These are universal questions, questions that any sufficiently advanced civilization would eventually ask. Maybe some civilization, far more advanced than ours, has solved these mysteries. Maybe they understand dark matter and dark energy. Maybe they've proven whether the universe is infinite. Maybe they found life on countless worlds. Whoa! If so, what would they tell us? What knowledge would they share? What perspective would they offer? We can't know, but we can imagine. And imagination, combined with scientific investigation, drives us forward. The mysteries that perplex us today might be solved knowledge to advance civilizations. Or perhaps they've discovered even deeper mysteries that we can't yet conceive. The cosmos is layered with mysteries. Solve one layer and you reveal another. Understand something fundamental and you see how much more remains unknown. This infinite regression of mysteries, each solution revealing deeper questions, is part of science's beauty. It means the adventure never ends. Understanding deepens forever. Imagine if we could speak with ancient astronomers, tell them about black holes and dark matter and cosmic expansion. Their minds would reel. What seemed impossible would become fact. Now imagine what astronomers 1,000 years from now might think about our current understanding, how limited it might seem, how naive our theories, how incomplete our knowledge. Yet those future astronomers will still face mysteries. They'll still be at the edge of understanding. They'll still be pushing boundaries. That's the nature of knowledge. It expands forever. The frontier is always ahead. And that's wonderful. It means there's always more to discover, always more to wonder about, always more to investigate. The mysteries of space aren't obstacles to overcome. They're invitations to explore. They're promises that reality is richer and stranger than we imagined. So embrace the mystery. Wonder about the universe. Ask deep questions. Seek truth. The universe is vast. The mysteries are deep. But the human spirit is even vaster. Our curiosity is even deeper. We have the capacity to understand. We have the drive to explore. We have the tools to investigate. The mysteries of space aren't something to fear, they're something to embrace. They're evidence that reality is richer than we ever imagined, that there's always more to discover, always more to wonder about. Throughout human history, we've pushed boundaries, we've explored new lands, we've developed new technologies, we've deepened our understanding of reality. And we're just beginning. We're at the frontier. The real adventure lies ahead. One final thought: every great scientist, every great explorer, every great mind that pushed understanding forward started exactly where you are, with curiosity, with wonder, with questions. They looked at mysteries and asked why. They pursued answers. They discovered truth. The universe awaits your questions. It awaits your discoveries. The mysteries of space are calling you today and forever. Will you answer the call and explore? Thanks for watching.